Just watched a video about photoelectric effect and how it works, and we are really happy. Now, let me give you a summary, and while I'm giving you the summary of this 20th century crisis, I will mention one last name, which is, well, his name is tricky, de Broglie. I will call him de Broglie. Okay? All right. So, okay. So what kind of crisis did we have? We have ultraviolet catastrophe, right? We have photoelectric effect, then we have heat capacity problem. I didn't talk about heat capacity stuff. Well, I think in my description I also don't talk about it, so never mind. Spectral lines, and finally radioactivity. Okay, so right when we enter the 20th century, there's a resolution to ultraviolet catastrophe by Planck, right? Planck's formula. Then Einstein uses it to particle nature of light. So let's write it. Einstein comes up with particle nature of light to describe this, and he uses Planck's formula, right? Then we can describe the problems in heat capacity with Debye, Einstein stuff. Okay, I will not talk about them, but it also uses Planck's constant. Then there is the Rutherford model. That brings its own problems, right? Let me call it electron falling to nucleus. That's the problem, right? So sometimes some resolutions bring some problems with themselves. And then there is Bohr in the middle of all this, who explains spectral lines using Rutherford model and says that electrons just simply don't fall. They stay in these orbits in the shells. And he uses Planck's formula as well, right? All this you can call quantum physics or modern physics. This could be called modern physics with all of its problems, and this is quantum physics. And the thing is that here there is an epiphany. Remember, light was a wave, right? Light was a wave, and then we described it also as a particle later on, right? How about, for example, matter, for example, electron, or matter in general? We know them as particle, right? Do you see what is missing in this table, 2 by 2 table? So light was a wave, but it now behaves like a particle. Electron is a particle. It takes a huge stretch of imagination, but de Broglie, which is the wrong way to read his name, talks about matter waves. So he says that everything has this wave-particle duality. Okay? So there must be an equation that describes these matter waves. That's where we step into quantum mechanics. So this is 1900s. This is 1910-ish, I think. This is 1925. So there's a 15 years of not seeing this. Okay? Because let's face it, thinking about light being a particle is less crazy than thinking about matter having a wave-like property. You know? Matter, which is like what you hold, it's how can it have wavy property, right? Okay. And once we have de Broglie, from that we have Schrödinger, Heisenberg, and this is already 1926, only 1 year later. And then later Dirac, which includes relativistic effects. Okay, I thought having this all together in one picture would help you figure it out. Let's talk about de Broglie matter waves. Okay. Yes. Well, Dirac wrote already in 1930 what? Can you look? 34? 1930s, he wrote book of quantum mechanics. And while we speak about quantum mechanics, we will need that Dirac function. So he devised it for that purposes. But by that time, quantum mechanics was pretty much complete. I think it's a few hundred pages with no illustrations.
It's better than some of the off-the-shelf books.
Okay. I believe you. Very good. De Broglie. What is de Broglie claiming in his thesis? And I think it was too much, and his thesis was about to be not accepted. But then Einstein read his thesis and he said, I see nothing wrong with this thesis. Okay? Although we see Einstein as someone who is opposed to quantum mechanics in modern day popular culture, as you can see, he's one of the first adopters of quantum mechanics. What he doesn't like is the interpretation. Okay? We will come to the interpretation. So what de Broglie is saying to us is that there is a wave side of matter as well, okay? And the energy of a particle, as Einstein described, is h times f, nothing new here. But the momentum should be h over lambda. Is this correct? So that's what he says. So he claims that there is a wave that accompanies every particle, including electron, proton, whatever you think about. And its wavelength is determined by its momentum. Okay? Now, this makes Bohr's model much more intuitive. Bohr's model becomes much more intuitive. Why? Because, look, do you remember this condition? Yes? Now it comes out as natural as it can get. Let me show you. You have an orbit, right? It has a radius of r. What is the length here? 2 pi r, right? Now you want to wait a moment. And de Broglie is claiming that electron also has a wave property. So let's fit that wave into this orbit. Are you with me? So I'm going to fit a wave into this orbit, but you see I couldn't fit it. It has to meet itself at some point. So then 2 pi r must be equal to n times lambda. Do you see why? So, for example, let's open it up. I'm opening it up. So this thing is something like this, and it's 2 pi r. So let me fit a wave here, right? And let me close it back. Now I close it back, and the wave looks like okay, let me make another wave. This one is better. Okay, I couldn't do it. Do you get it? Let's make a wave that is way more. Yeah, there you go. Are you happy? Yes. So n lambda has to fit 2 pi r. And since lambda is h over p, the momentum, 2 pi r equals n times h over p. P times r is equal to n times h over 2p. mvr equals n times h bar. You get the same thing in a much easier way. Do you see it? Are you happy? We usually teach it together without separating the two things. We say, look, mvr equals nh bar. You don't get it? Okay, think about it like a wave fitting in the orbit, but there is 15 years in between. Okay? All right, very good. Now that you start talking about matter as a wave, only 1 year later you have the equation for it. Right? So, drum rolls, please. Thank you very much. Quantum mechanics. Now I will stop doing this history thing, and I will just describe to you quantum mechanics together with its particular interpretation, the interpretation that Einstein didn't like. So the interpretation that I'm going to follow will be Copenhagen interpretation. Okay? All right. So according to quantum mechanics, we have something called wave function. Instead of system being described, let's say you have a particle in a system, and classically you would describe it with position and velocity, right? And some interactions. Once you have interactions, position and velocity, you know the future. In quantum mechanics, the thing that describes the system is not position and velocity. It's something called wave function, and it contains all information that can be known about the system. No, it contains all information about the system, but we can't pick into the wave function all of it. Like when we look at the wave function, it will change. Okay, so in paper, it has all the information that the system can have, but when you interact with wave function, when you measure something, it changes. It adapts to your measurement, so it will be tricky. What is this wave function? We will show it with this weird letter, psi. And it's a complex valued function. Okay. Do you have a question so far? So, very good. Okay. When we are not looking, when we are not looking at it, by looking I mean measuring, interacting, etc., things propagate. That's an important word, propagation. Propagate according to the Schrödinger equation. Okay. Here comes the equation. Ready? I h bar del psi over del t equals to negative h squared over 2m del squared psi over del x squared plus Vx psi.
Can we be time dependent?
No, not in this course. In this course, V is not time dependent. V is constant with time, okay? In this course.
But in general, it's time dependent.
Generally, it's time dependent. Okay? V is the potential energy. So in general, potential energy could be time dependent. Schrödinger equation is deterministic. That's an important word. You know, that means you know psi of xt given psi of x0. So you can know what the wave function will do if I give you the wave function right now. Okay? Do you have any questions so far? Okay. So it's all part of the package, Copenhagen interpretation package. Here is a sub-package in it, Born statistical interpretation. So you might be asking, okay, let's say I accept what psi x of t is. It's a function, but what does it mean, right? Well, we will gain a lot of different information from this, but one of the early informations that you need to know is that if I take the absolute value of xt, take its absolute value squared, integrate it over a certain region, going from A to B, then it will give me probability of finding the particle between x equals to A and x equals to B. Okay? So we have a function that evolves with time, obeying a certain equation, and it's deterministic. What is not deterministic and perfectly probabilistic, okay, is what it can tell us. For example, right now, let's say the wave function looks like this. Okay, this is psi of x squared at right now. So we can say that particle is more likely to be here, and less likely to be here. And the likeliness actually depends on this amplitude. It's proportional to that psi squared of x. Okay? But particle has to be somewhere, right? There's a probability, yes, but let's say particle needs to be somewhere. That brings us some constraint on the wave function. Our wave function needs to be normalized at all times. So at all times, whenever I integrate psi of x t squared dx, needs to give me 1. Because probability of being here, probability of being there, probability of being there has to add up to 1, so that the total probability is 1. So far, so good? Do you have any questions? So it tells you everything there is to know, but it does not include a precise position. We only have a statistical interpretation. Okay? Now, I do a measurement and find particle at x equals to c. I'm not talking about the probability now. I did the measurement. I found the particle to be at c. Okay? What happened to all your quantum mechanics, probability, and whatnot? Well, there are two views here. The realist, which always loses, okay, says that the particle was there all along. The particle was at x equals to c, and you measured and you found it there, right? But Copenhagen interpretation tells you something else. Copenhagen interpretation tells you that the wave was propagating like this. This is the propagation stage. All right? And then you did the measurement. Measured at x equals to c. What Copenhagen interpretation tells you is that the wave function needs to be collapsed. Okay, this is the famous x equals to c, that particular point, and this is the measurement stage. Here's what's missing in Copenhagen interpretation. We don't have an equation that governs this wave function collapse. First of all, let's talk about collapse. Why does it have to collapse for it to be consistent theory? Why does it has to collapse? Have to, has to, whatever. Like, the wave function needs to collapse. Do you have any idea why?
Because of the uncertainties. Time is going through.
What?
Time is going through. For example, if you mention, for example, one time, there is not t plus delta t, and another thing we don't know exactly.
Very good point. You are very close to what I have in mind. So let's say I have measured it and it's at C, at a particular point. Then I do the measurement right after that, immediately, okay, not waiting any more moments. So the particle cannot go with speed of light, right? It has to be a local theory somehow. The particle still needs to appear there, wherever I measured it. You can do this measurement in principle arbitrarily fast, right? And the particle needs to be there. It can't just jump somewhere else.
But if you do it fast enough, you can actually localize the particle there. It's called Zeno effect, quantum Zeno effect.
Okay, let's not go into deep stuff. We can always smear all this and stuff like that. But my point is that you measured it there. Just because we say that wave function has this probabilistic side, which tells you that if it's like this, it can be this much here, this much here, this much there. But once you did the measurement, it's 100% there. So the wave function needs to adapt to that being 100% there. Does it make sense? Let's say you have some ambiguity in your measurement, then at least the sum of the wave function in that region has to add up to 100%. That means that you need to have a Gaussian at least localized there. Does it make sense? That's why it needs to collapse. But now we have a schizophrenic theory. When it propagates, it obeys Schrödinger's equation, right? But when I measure, it stops obeying Schrödinger's equation and does something weird, which is collapse, right? So there's a problem here. And this is after all this weirdness, it solves all those other problems, like why harmonic oscillators has to have certain energies. All of those problems are solved with Schrödinger's equation. Now we remain with ultimate problem, which actually questions our very reality. There is this wave function that is running in the background, and as you can see, you can't actually directly measure the wave function itself that has all the information, because when you ask a question to wave function, it adapts to your answer. It adapts to your question.
You cannot measure the whole wave function.
Yes.
You cannot.
You cannot. I tried to say cannot. You can't. I said you can't. You can't measure. Let me rephrase it further. You cannot measure the whole wave function, okay? Because when you try, it adapts to your question. Okay? I even have a statement here. I use stronger words here. You can never measure wave function itself. Aklım waffle'a gitti galiba. Wave function itself. Okay?
We should only measure the square root.
Say it again.
We can measure the square root of it. I mean the probability of being.
Sort of not even that. Let me tell you how. So, how do we now see the double slit experiment? How do we see it now? After all this quantum mechanics and stuff, right? We see it in the following way. Light is tricky, so let's send electrons. Okay? Electrons are also waves. By now, this is not weird at all, right? So you send an electron, and an electron is a wave, right? And it propagates as a wave as long as we don't detect it. So once the wave reaches here, it already has the double slit experiment profile. Its psi squared, its psi started as a plane wave, went through the slits, turned into, so the electron is passing actually from both slits because it's a wave, right? It can do whatever it wants. It's like the robot in Terminator 2. You remember that? The guy could go through these bars and stuff like that and would emerge on the other side. The electron is doing something as weird as that. So it comes out, it's a wave, it comes, and we are going to detect it. What do we detect? We detect an electron here. Okay? What happened to its wave function? It collapsed. Okay? But now we send one by one, single electron experiment. So we send one electron, it appears here. We send another one, it appears here. Another one here, another one here, another one here. Then we accumulate all this data and sum up, and we get this probability distribution. Do you see what is going on? So we couldn't do it for single electron. We couldn't measure it everywhere. Somehow, like, we couldn't get the whole wave function. But what we did is we did an ensemble average of all the experiments. Okay, we did same experiment trillions of times and summed up all the possibilities, all the outcomes, and that draws us the wave function that reached there before collapse. Does it make sense? No, doesn't?
No, it makes sense, but I'm wondering, does it also explain the Heisenberg?
Yes, absolutely. Absolutely.
You said that we couldn't see the ordinary method as wave duality, but actually there is a nice intuitive way of
Yes.
thinking about that. You know that from the basic electrical engineering, the waves can only interact with the things that are a similar size. So if you consider for an electron matter wave, it's actually relative to its size, but for a human, our matter wave is about 10 kilometers, 20 kilometers in radius, so we couldn't actually see our wave nature, but actually you can see it in the microscopic scale. It's actually coming from that.
You can see the microscope, the wave function.
No, I mean that wave matter duality.
Okay. Yes. The way that I understood it is that these quantum effects are more pronounced on the nanoscale. So nanoscience and nanotechnology, right? That was the course. That was the name of the course. Good. We mentioned it. Let me talk about Dirac delta function that we discussed a little bit. Dirac delta function is what you get after your position measurement. It looks like this. It's a mathematical structure that is needed to be defined. So it's like a spike. So this is x equals to a, and this function is Dirac delta x minus a. What Dirac delta tells you? Dirac delta function is 0, no, it's infinite at x equals to 0, and it's 0 otherwise, but at the same time its integral is 1. Oops, that's 0, 1. Do you understand this function? So whenever, at the moment where it's spiking, it goes to infinity, right? Other places it's 0, but despite the fact that it goes to infinity, that part is so narrow that it adds up to 1. Not to infinity, but 1. It's like a very, very squeezed Gaussian. Extremely squeezed Gaussian. So it's a Gaussian where you take what was it? The spread, standard deviation to 0. All right? Any questions? So this is what happens to a wave function after ideal measurement of position. It collapses into a Dirac delta. Okay, good. What we will get is explanation to all the previous stuff with quantum mechanics. What will remain unresolved, unsolved is this measurement problem. Okay? Take care.